This is the video for section 11.7, Strategy for Testing Series. And the point of this section is to put together all the techniques that we've developed in the previous sections in order to understand series in general. And just like with the strategy for computing integrals, we have sort of a hierarchy of ways of thinking about series that you might come up against. And I'm simply going to summarize the strategy that's listed on page 739. That's the first page of the section 11.7, and it goes like this. So we're simply going to go through the line of options that we have. So if you see something that looks like summation over n, 1 over n to the p, then this is a p-series. Right? And we know exactly when those converge and exactly when those diverge. And similarly, if you see anything like summation n r to the n, right? Now notice the difference between this and the one in item 1 here is that in item 1 the n is in the base of the exponent, and in the second one the n is the exponent, right? And this is one of our geometric series, and we know exactly how those converge from the section 11.2. Item 3, so 1 and 2 are if the series is in something that you immediately know what to do with, then do that thing. Item 3 says, well, if your series looks like one of those, right. So if your series looks like it really wants to be a p-series, or it looks like it really wants to be a geometric series, then you should use the comparison test or the limit comparison test with the series that your series looks like it wants to be. And in a minute here I'm going to go through some examples so that we can see exactly what I'm thinking about with these. 4, if you look at a series and it looks sort of funny, so if the limit as n goes to infinity, an is not 0, right? So if you're trying to add up a bunch of terms and the terms don't get arbitrarily small, then you want to use the test for divergence. If you have a series that's of the form -1 to the n bn, or -1 to the n minus 1 bn, well, this is one of your alternating series, so we would use the alternating series test. Six, if you have factorials or products, powers, then you would want to use the ratio test. Or if you have some big something to the nth power, then you would want to try the root test. And then the last piece in the strategy is that if you recognize that you have a function that you can integrate, then you want to try the integral test. And don't forget, and this is really, 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 really important, that each of these tests comes equipped with a certain number of hypotheses, right? So if you want to use the alternating series test, for instance, then you need to make sure that these bn's are positive and non-increasing, etc., etc. Okay. So let's look at a couple of examples in this form. So for instance, if we want to look at the summation -1 to the n over n squared plus 2. Right. So you see here the power of -1 that's occurring inside the sum. So, right, -1 to the n tells you that you want to use the alternating series test, which I'll abbreviate as AST. And in these examples, what I'm going to do is I'm going to go through and I'm going to give you an idea of how you should approach the series, and then what you should do is work through each of these series to check and see that the test applies and to see what sort of conclusion it gives you. This one, the alternating series test, will allow you to conclude that the series converges. Next example is the summation over k, 2 to the k times k factorial over k plus 2 factorial. And for this one, you see that you have some nice exponential expressions and some factorials. And so you would want to try the ratio test for this one. Let's see, another one here would be, excuse me, the summation over k of 1 over k times the square root of k squared plus 1. That's a k squared plus 1. Inside the square root. And if you look at this one, so it doesn't technically fit into one of the p-series formats, but it's very similar to one over k times the square root of k, which is the same thing as summation over k, 1 over k to the 3/2, right? And this one is a p-series with p equals 3/2. So it diverges, and then you would want to compare that, or limit compare it, to the original series. Because we only took that p-series is only very similar to the one that we started with. Maybe two more exotic examples. So something like the summation over k of 1 over 2 plus sine of k. Now this one's interesting. So it doesn't look like a p-series because there's no exponent. There's no exponent, so it's not geometric. So 1, 2, and 3 are out. It's definitely not alternating. There's no factorials or powers, so it's not a ratio or a root test. And that doesn't look like a function that you know how to integrate. So the only thing that's really left is the test for divergence. And the key there is to recognize that when you take the limit, as k goes to infinity of that kth term, Right, the thing is that sine k bounces all around between values in between plus or minus 1. And so this 1 over 2 plus sine k has no limit. And from that you get to conclude from the test for divergence that the series diverges. In order for it to converge, it would have to have a limit of 0 for the limit of the kth terms. And we'll do one more and we'll be done. So last example, I want to look at the summation over n of e to the 1 over n divided by n squared. Now this one's sort of funky like the previous one. It's sort of got a piece that looks like a p-series, that 1 over n squared. It's got a piece that looks sort of like a, I don't know, some sort of a geometric bit on top. But either one of the pieces is, since it's got both those pieces, it really isn't either one. But what you can see is that the numerator, as n goes to infinity, has its limit, well, it goes to e to the 0, which is just 1, and that denominator has its limit at infinity. And what that says is that as n goes to infinity, this e to the 1 over n squared is really behaving like 1 over n squared. Okay? And so what that tells you is that you might be in a good position to use either the comparison test or the limit comparison test. Personally, I would use the comparison test with the summation n e over n squared. This one converges because it's a multiple of a p-series with p equals 2, and if you do a direct comparison, you can conclude that the original series converges as well. Okay. Now, in each of these examples, there's a lot of details that I'm sweeping under the rug. What I want to do is I want to give you a snapshot, an idea of how this strategy works in general. And that's the end of the lecture on section 11.7.